Welcome to today's webinar. My name is Chloe, and on behalf of Oxford Global, I would like to thank you all for joining us today. Today's webinar, Fast Track Formulation with Biologics Screening in a Snap, is brought to you by Ross Walton, Senior Application Scientist for Analytics at Unchained Labs. After the presentation, we will then lead into a Q&A. Please submit your questions throughout the webinar using the Q&A feature. The full recording of this webinar will be made available to download on our website, and the details will be sent to you after the webinar. Let's begin. Ross, over to you.
Great, thanks, Chloe. And hi, welcome everyone to where to my talk. I'm going to be talking to you about how you can fast track formulation screening of biologics. So one of the events that I really enjoyed watching this year at the Olympics was the track cycling events. For those of you who haven't seen it before, the way the race works is that the first part of the race is all of these cyclists very carefully and methodically jockeying for the best position on the track. Then, as soon as the starting guns goes off, they race around the track as fast as they possibly can. So to me, that seems a little bit like how you might set up a big experiment, like a formulation screen. You design the experiment very carefully and very methodically, but once you're ready to execute, you want to get it moving as fast as you possibly can. And just like with cycling, having the right team makes that process a lot easier. Unchained Labs brings together 4 instruments to make the dream team for doing high-throughput formulation screens of biologics. First, we have Stunner, which measures the concentration, sizing, and polydispersity of up to 96 samples at a time. Then we have Unagi, which is a fully automated benchtop buffer exchange platform that uses really gentle UFDF to do buffer exchange and can also concentrate your samples. Uncle is a thermal stability platform, which looks at the melting and aggregation of biologics in different formulations. And Honeybun measures the viscosity of up to 10 samples at a time in 3 minutes with no cleaning and basically no setup. So for the case study I'm going to share with you today, we took 4 different antibodies, 2 of which are FDA-approved therapies, and reformulated them into 4 different formulations. Each one of those different formulations had the same buffer component, as well as had polysorbate 80, but they all had different excipients. Sodium chloride and sucrose are 2 excipients that are really commonly used in a lot of different biologics formulations for controlling osmolarity. And then arginine often gets added to formulations in order to reduce their viscosities, especially of those high concentration formulations that might be applicable for subcutaneous injections. The first step for running this particular formulation screen was to get everything into the correct formulations at the right concentrations. And that's where Unagi came in. Unagi has flexible sample throughput of up to 8 samples and can handle a wide range of sample volumes, anywhere from 450 microliters to 8 milliliters. Setup is simple, takes less than 15 minutes of hands-on time, and best of all, once you set things up, you can just walk away from the instrument and Unagi will handle the rest. Also, Unagi will actually send you a text message when the buffer exchanges are finished. So you don't even need to be anywhere in the room with the instrument. Unagi works great with high concentration proteins as well. Most of the buffer exchanges I conducted at 10 milligrams per milliliter, but I did also end up concentrating some of these samples up to 100 milligrams per milliliter, and Unagi was able to deal with that just fine. Unagi uses a positive pressure UFDF system, or ultrafiltration diafiltration system, with individual volume tracking and an adaptive filtration cycle, as well as has a programmable pressure level for very fast, very gentle UFDF. When you load your samples into Unagi, the instrument measures their volume, then pressurizes those samples, which forces the buffer that's already in the sample down through the bottom of the consumable, which we call an UNA, through a membrane filter. Then, once it's after it pressurizes, Unagi measures the volume again and adds and refills it with the new buffer. Unagi does these cycles over and over again until it gets to the percent exchange that you set up during the experimental design. As a last step, which is optional, Unagi can also do a final concentration step. During the pressurization cycles, Unagi is also orbitally mixing the samples, which prevents membrane fouling and also prevents dead-end filtration, which keeps the samples homogeneous and actually speeds up processing time quite a bit. So once our buffer exchanges were finished, the next step was to check and make sure that the samples were at the correct concentration and that they were still intact, non-aggregated, and happy in their new formulations. For that, I used Stunner, which is a plate-based system that measures the concentration of proteins, as well as their size and polydispersity from just 2 microliters of the sample. It finishes a full 96-well plate in just about an hour. As a bonus, Stunner can also determine the second virial coefficient, or B22, and the diffusion interaction parameter, or KD. These numbers are very useful for predicting if a monoclonal antibody is likely to aggregate as you increase its concentration in its formulation. And that's particularly important when you're thinking about subcutaneous delivery of the monoclonal antibody, which tends to be done at much higher concentrations than an IV infusion. Stunner uses UV-vis absorbance to determine the concentration of a protein in a sample based off of the absorbance of that protein at 280 nanometers. So that answers the question of how much a sample or how much protein do I have in my sample, which is important. But it's also really important to know, especially after buffer exchange, exactly what is in the sample, like whether or not you've got any aggregates in the sample. Stunner uses dynamic light scattering, or DLS, to determine the size and distribution of particles in a solution. DLS is extremely sensitive to large aggregates that will sometimes show up if a protein isn't completely happy with its formulation. By looking at the average hydrodynamic diameter of all of our monoclonal antibodies in their new formulations, after buffer exchange, obviously, and also looking at the PDI, or polydispersity index, we can see that adalimumab aggregated when it was exchanged into sucrose. Intact monodispersed monoclonal antibodies tend to have diameters at around 10 nanometers, and PDIs tend to be less than or equal to 0.1. And you can see adalimumab, its average size is quite a bit higher than 10, and its PDI is also higher than 0.1. These large values like this may indicate that the protein is aggregated. That means we can actually eliminate this formulation completely from the rest of our studies because it's clearly a bad combination of excipient and protein. But you may also notice that there are a number of samples here which have a pretty much as expected average size, but their PDIs are pretty high. You may also be noticing that it's mostly the sucrose-containing formulations that have this phenomenon. To explain those results, we're going to need to look a little bit closer at Stunner's DLS results. And for those of you who are curious, may also be interested to know that I also looked at the concentrations of these samples and found that all of them had better than 90% recovery from the buffer exchange process. So the reason for those PDIs can be seen in these intensity distributions. Sucrose appears as a peak in the DLS intensity distributions at about 0.8 nanometers. And you can see that that same peak does not appear when this monoclonal antibody, MAB1, was formulated with sodium chloride. It also didn't appear when it was formulated with arginine alone. PDI is a summary statistic that lets you know how wide the total particle distribution is of a sample, but it doesn't necessarily tell you about individual populations within that sample. Mass and intensity distributions, and also number distributions, tell you more about the specific populations within a sample. When I checked the distributions of all of the other MABs in the sucrose solution, I saw exactly the same peak, that 0.8 nanometer sucrose peak, and then a second peak at about 10 nanometers. That tells us that all of our monoclonal antibodies were very happy in our chosen formulations, with the exception of adalimumab, which we saw earlier. Stunner combines this concentration measurements with DLS to look at KD and B22 of formulations, which it determines by graphing the concentration of a dilution series of a monoclonal antibody in the formulation with a couple of different DLS outputs. B22 and KD are values that come from the slope of the line that gets fitted to these graphs. A positive slope is indicative of repulsive forces between the protein molecules. A negative slope and a negative KD and B22 value is indicative of an attractive force. So when you're looking to reduce the propensity to aggregate of a monoclonal antibody, what you're looking for are positive and large values of KD and B22. So you can see here that MAB1, which is in blue, or MAB1, which all of these are MAB1, really liked being formulated with sucrose, which is in blue. You can see the KD and B22 in that table there are both positive and fairly large, whereas all the other KD B22s, all of those other slopes were negative. In this table, we've highlighted the largest value of B22 and KD, which indicates the formulations for each one of those monoclonal antibodies that is least likely to aggregate as we increase the concentration. MAB1 and trastuzumab both preferred to be in sucrose, whereas MAB2 seemed to like that combination of arginine and sucrose. And adalimumab really didn't like any of the formulations we tested. B22 and KD for all of the formulations with adalimumab were negative, and arginine alone gave the highest KD value, but the combination of sucrose, arginine alone gave the highest B22 value, but the combination of sucrose and arginine gave the highest KD value, which I've highlighted there in yellow. The end result of all of this is that for MAB1, MAB2, and trastuzumab, we have formulations which are unlikely to aggregate, even when the concentration for the protein goes a lot higher. And that's useful if you want to evaluate the developability of the formulations or figure out which one of those formulations is really optimal for each of these monoclonal antibodies. So now that we know we've got some happy proteins that are in their formulations, and we've done some non-destructive testing, we're going to turn our attention instead to stability testing. Unchained Labs is all about providing the right tools for biologics, and UNCLE was the first all-in-one biologic stability platform. UNCLE monitors 3 critical stability metrics: unfolding, aggregation, and sizing. It can do that because it has and has always had 3 different detection methods within the instrument: fluorescence, static light scattering, and DLS. These 3 detection methods, combined with the temperature control from 15 to 95 degrees Celsius, give UNCLE over a dozen applications for looking at all kinds of samples. And for all this, UNCLE still only requires 9 microliters of sample. So this is what the raw data from an UNCLE experiment looks like. The fluorescence spectra get recorded as the temperature increases. And you can see that as the temperature increases, the fluorescence of the protein changes while it is unfolding. As the aromatic residues come in contact with an aqueous environment, the fluorescence maximum decreases and shifts to the right, which is known as a redshift. Because UNCLE records the full spectrum of fluorescence, it's flexible and can handle samples that might show a blue shift, which would move the peak over to the left instead, or don't show any wavelength shift from the emission peak at all. Full spectrum fluorescence is also where we take the SLS signal, which assesses aggregation and increases as the protein aggregates. UNCLE quantifies this shift in a MAB's fluorescence using the barycentric mean, or BCM. From there, we can determine melting temperatures, or TMs, at the inflection points of these BCM curves. When we do this for MAB1 in the 4 different formulations, sodium chloride, sucrose, arginine, and sucrose and arginine, we found that the addition of either sucrose or arginine increased the melting temperature of the protein by about 3 degrees Celsius relative to sodium chloride. However, we also found that this effect was not cumulative. The combination of sucrose and arginine had a TM that was really close to the TM of sucrose or of arginine alone. You can see the yellow dot very close to the temperature of both the light green and the blue dots, but higher than that gray sodium chloride dot. If we add in this SLS signal and then also use that to determine the temperature of the onset of aggregation, or TAG, we can see a few additional things about each of these formulations. So first, sodium chloride, that we see in gray, had the lowest TM, but actually had a TAG that was pretty comparable to the TAG in sucrose, shown there at the bottom in blue. However, sodium chloride also caused much more extensive aggregation. You can see that the gray solid line is a lot higher than the blue solid line. Higher SLS signals are indicative of a larger extent of aggregation. So sodium chloride is actually, even though it's starting to aggregate at about the same temperature, the aggregation is much more extensive than with sucrose alone. Also, you may remember that based on TM alone, we really couldn't differentiate which formulation was the best between sucrose, arginine, or the combination. But if you add in the TAG and SLS data, we can actually see that sucrose alone is extremely beneficial. Even though the T-ag for arginine was higher, the light gray versus the blue, the SLS signal of arginine was also a lot higher than the sucrose. So sucrose had the lowest overall SLS signal, which indicates that it also had the lowest extent of aggregation. Now, SLS is proportional both to size of particles in solution, but also their number. So it's really useful to have an orthogonal method of looking at aggregation. And that's where DLS comes in. When we compare the DLS results of MAB1 in sucrose with the results from sucrose and arginine, we can see that at 20 degrees Celsius, at the beginning of the thermal ramp, both of the MAB1 was pretty happy in both of these formulations. There was a single well-defined peak at about 10 nanometers, exactly as we'd expect. However, when we heat up these samples to 90 degrees Celsius, you can see that the peak in the sucrose plus arginine sample shifted really far over to the right, got a lot bigger, with an average of somewhere between 200 and 300 nanometers. You can also see that that peak is a lot higher, but it's also a lot wider, which indicates that there is a much wider distribution, with a much more heterogeneous combination of aggregates. In sucrose, on the other hand, the peak didn't shift nearly as much and didn't get nearly as wide, indicating that the sucrose was actually preventing aggregation, at least to some extent. We did this same stability screen for all 4 of our MABs in all 4 of our formulations at 2 different concentrations, 1 milligram per milliliter and at 10 milligrams per milliliter. The TM, TAG, and DLS results that I'm showed with MAB1 all came from a single thermal ramp experiment, and we have that data for all of our other formulated combinations of MAB and formulation as well. UNCLE delivers an extremely rich data set that can be used to clearly identify the relative stability of MABs and formulations. When we bring together all of UNCLE's stability data, we found that sucrose alone was the most stabilizing excipient for MAB1 and for trastuzumab at both of the tested concentrations. Interestingly, MAB2, the combination of sucrose and arginine, was more stabilizing at 1 mg per mil, while arginine alone was more stabilizing at 10 milligrams per milliliter. You may also remember that MAB1 and trastuzumab had positive B22 and KD values with sucrose, while MAB2 had a positive KD and B22 values with the combination of sucrose and arginine. So sometimes, like you can see here with MAB2 and with sucrose, or like you see here, sometimes certain formulations, certain antibodies are more stable in a formulation at one concentration, but not as stable in another concentration. So when you're changing concentrations of MABs, it can occasionally be necessary to reformulate your monoclonal antibodies. Because UNCLE can handle samples and measure their thermal stabilities of samples at concentrations anywhere from 0.05 up to 300 milligrams per milliliter, depending on the protein, you can use the same instrument to do those thermal stability studies at whatever is the most relevant concentration for your specific application. When we take the TM and TAG data of our 16 different samples and color them according to antibody instead of coloring them according to formulation, we can see actually a few interesting things. So first, MAB1 and trastuzumab behaved very similarly and tended to be the most stable. They had the highest TMs and the highest TAGs, and you can see that the two green colors, dark green and light green, are there clustered at the top right of the graph. You can also see that MAB2 generally had the lowest TM and TAG. It's shown in blue, as at the bottom left corner, and then adalimumab had TMs that were similar to MAB1 trastuzumab, but TAGs that were more similar to MAB2. So it's down there at the bottom right corner. When we take those same formulations and then regraph the data from the 10 milligram per milliliter sample, we can see that MAB2 in blue and adalimumab in yellow actually got more stable and significantly more stable at the higher concentrations. All of those points shifted up and to the right. Now, that's a little bit of a surprise because the more typical assumption is that stabilities tend to get worse at high concentrations, but at least with adalimumab and MAB2, that was clearly not the case. They actually got more stable. That means that it's even more important to check the stability of formulations at their most relevant concentration. So if you're going to be doing something with really high concentration samples, it behooves you to check the stability at higher concentrations. So 1 milligram per milliliter and 10 mg per mil stability tests are great for mAbs that are going to be delivered by IV injection or for just general developability testing. But since subcutaneous injections tend to go a lot higher, it behooves us to check and make sure that the formulations that got the green flag at the low concentration are still the best bet at those higher concentrations. Since high concentration monoclonal antibodies tend to have the biggest issues with aggregation and with viscosity, that's where we'll be focusing. When we use UNCLE to look at the aggregation of mAb1, mAb2, and adalimumab at 100 mg per mil, we can see that generally the T-ags were actually slightly lower at 100 mg per mil than they were at 1 or at 10 mg per mil. But we can also see quite clearly that mAb1 still likes being in that sucrose solution, while mAb2 and adalimumab actually prefer being in a combination of sucrose and arginine. Those are the three highlighted formulations that had the highest T-ag for the respective antibodies. You can also see that the mAbs aggregated extremely readily in sodium chloride, just like they did when they were at lower concentrations. So sodium chloride, probably not the best excipient for these three specific antibodies. Viscosity is another big issue for high concentration biologics, both for manufacturing and for delivery. But it's difficult to measure, so almost no one does it as often as they should. It takes a long time and usually involves a lot of sample prep or a lot of cleanup steps. Honeybun is the only viscometer built to solve this problem. Honeybun can take 10 samples at a time and in a few minutes get you viscosity data. And it does this using only 35 microliters for each sample in a typical run and as little as 15 for a low volume run. Honeybun can also run a full range of viscosities from 0.5 up to 150 centipoise, which covers the basis for a lot of monoclonal antibody formulations. Sample prep is really quick too. All you have to do is pipette the sample into the consumable and then work through some very quick, very simple software steps. And lastly, Honeybun is also able to measure the viscosities of samples from 4 degrees Celsius up to 45 degrees Celsius. So if you're curious how low temperatures are going to influence viscosity, that's something you can actually check with Honeybun. The way the Honeybun works is that once the samples are inside of Honeybun and the wells that the samples are in are pressurized, and the sample gets pushed through into a resistance channel, which we have marked here as R. The pressure that Honeybun applies is delta P. Now, you might notice that the resistance channel is much smaller than the measurement channel marked in M, even though it's a single continuous channel. The reason for that is that this allows the channel to have a high resistance to flow in one section of it, but also allows for Honeybun to determine the flow rate through the channel, called Q, with just a camera, with monitoring, just looking at that camera. Since viscosity is defined as resistance to flow and is the quotient of shear stress and shear rate, Honeybun can find the viscosity by dividing delta P, the pressure, by the flow rate then measured, Q, through the microfluidic channel, and combining this with some constants from the dimensions of the resistance channel, its length, its width, and its height. The calculations are done within Honeybun. So if all you're interested in is the viscosity, you get a single number output. That's what you care about. If you're interested in some of those other values, they're also output by Honeybun. But for now, we're just going to be looking at the single viscosity value that we got out of Honeybun. When we measured the formulation viscosities at 100 milligrams per milliliter, we found that, generally speaking, formulations containing sucrose were more viscous than the ones containing arginine or sodium chloride. And that makes sense. I mean, sugar-containing solutions tend to be a lot more viscous than non-sugar-containing solutions. However, the interesting thing is that we also found that the addition of arginine increased the viscosity of mAb1, but it decreased it for mAb2. Now, I know it's pretty typical to add arginine to formulations in order to reduce their viscosities, but that really isn't going to be appropriate for every single monoclonal antibody. And so it's important to check and also to check at the concentrations that are most relevant to you. By taking all the data we talked about, Sunders B22 and KD results, UNCLE stability data at the different concentrations, and then Honeybun's viscosity data at 100 milligrams per milliliter, we can crown clear formulation winners for at least a few of our monoclonal antibodies. mAb1 and trastuzumab were happiest when they were in sucrose alone, whereas mAb2 was happiest when it was in a combination of sucrose and arginine. Now, sadly, really none of the excipients did a great job of stabilizing and preserve and making adalimumab happy. So I'm afraid it's disqualified from this winner's circle, but it can always come back and try again. Before I go, I want to leave you with one last thought. Sometimes we all feel a little bit like snails and are a little bit slow, and we're trying to do really complicated experiments. But with the right equipment, anyone can go fast. Thanks for your attention. Thank you for attending this talk, and I'll be happy to take any questions now.
Thank you very much, Ross, for your presentation. As he mentioned, we'll now open the floor to discussion. Remember to send your questions in using the Q&A feature. So we have a question: how much protein solution can the UF-DF process be conducted using the Unagi instrument at a time? So they're asking about the volume range.
Right. So each one of the UNAs, that's the consumable that's in Unagi, can handle between 450 microliters and 8 milliliters. And there's 8 of those UNAs within a single experiment. However, there is also another option within the experiment, which we call reduced sample volume, in which basically the instrument is taking protein samples from a reservoir, putting them into the UNAs, and then sequentially increasing the concentrations. So generally, I'd say 8 by 8, but there are cases where it's handling up to 50 milliliters at a time. So it depends a little bit on the exact experimental design and exactly what somebody's trying to do with it. But for simplicity's sake, 8 consumables, 450 microliters to 8 milliliters.
Perfect, thank you. Can we also use Unagi for the UFDF of nanoparticles?
Oh, yeah. So we actually have done some experiments with doing that, and it does work. So certain lipid nanoparticles specifically, other materials, we haven't done as much testing, but I think it might be possible. So we have done testing with lipid nanoparticles, and we have gotten successful buffer exchanges. It's a little bit more of a complicated process than with proteins. They tend to be a little bit less stable, a little bit more prone to sticking together. So, best thing to do is to reach out to our info@unchainedlabs.com email address, talk to some of our scientists, and we can figure out probably the best way of setting up those lipid nanoparticle buffer exchanges.
Perfect, thank you very much. Is there a larger version of Unagi that can handle higher throughput?
So yes, actually there is. It's called Big Tuna. I like to think of it as Unagi's bigger brother. So in that case, it's using a plate-based system rather than the individual consumables that we talked about earlier, but more or less functions the same way. Still positive pressure driven and still using those membranes. So the plates, there's 2 different options for the plates in Big Tuna. You can either get a 96 well plate. In the 96 well plate, each one of the wells, I think, is about 500 microliters maximum volume. And then there's also the 24 well plate, which is essentially the same internal dimensions of each of those wells as the UNOs. So each one of those can handle up to 8 milliliters. So for those bigger runs where you've got more samples, lower volumes, a lot more samples, but at lower volumes, or you just have a lot more sample generally, Big Tuna is probably going to be fill that niche really well.
Perfect, thank you. And I'll just remind everybody, please submit your questions using the Q&A feature. So another question, can the systems be used in QC or a GMP environment?
So yes, they actually can. So with Stunner and with OnCall, there's actually a 21 CFR Part 11 compliant software package that you can add on and use for audit trails and so forth. And for all the other instruments, we do have customers who have gotten them into their QC, as well as not necessarily GMP. That's more for our Sunny suite. That's more for our lipid nanoparticle manufacturing devices. But we have people who have gotten them into QC or GLP settings, so other regulated settings. So again, absolutely fits there, and we can help that process along however is necessary.
Perfect, thank you very much. What consumable does Uncle use?
So Uncle uses a little consumable that we call the Uni. I sadly don't have an example on me right now, but it basically consists of 16 cylindrical quartz cuvettes that are open on either side, assembled into this black metal frame. So each one of those cuvettes takes 9 microliters of sample. The spacing is actually the same as the spacing of a 384 well plate. So if you have multi-channel header that is set up for 384 well plates, it'll work with the unis. And then once you have your samples filled, you lock it into a little frame, place it in the instrument.
Perfect, thank you. You'll have to forgive me for my pronunciation. So we have another question. So about the performance differences between MABs, please could you remind me the trastuzumab sucrose arginine values?
Oh, sure. So in this particular situation, the let's see, the sucrose I believe was at 80 milligrams per milliliter, and then the arginine was at 10 milligrams per milliliter. And then with the combination of sucrose and arginine, we kept those same concentration values. We just mixed them together. And that wasn't just the case for trastuzumab. That was the case across all of our formulae of all of our monoclonal antibodies. So all of them were in the same formulation. They all had 80 milligrams per milliliter sucrose, 10 milligrams per milliliter arginine.
Perfect, thank you very much. What other kinds of samples can your instruments handle?
Oh boy. So a lot is the short answer, I'm afraid. So pretty much for all of our instruments, we've tested them with fabs, we've tested them with engineered and recombinant proteins, we've tested them with nucleic acids, both mRNA and DNA. We've tested them with lipid nanoparticles. We've tried out viruses. We've tried out certain small molecules and as well. So each one of them can function with a wide variety of different samples. There are specific requirements sometimes in terms of like organic solvents and things of that nature. All of that we have documented on our website, or if you reach out to me, I can provide that information.
Lovely, thank you very much. Are any of your instruments suitable for ultra high concentrated products? Excuse me. For example, 100 milligram milliliter pre-filled syringe formulations.
So Center can measure 100 milligram per milliliter solutions. I've absolutely done that multiple times, getting both the DLS results and the UV-Vis results. Honeybun, as I showed you, works great with 100 mg per mil samples. Uncle as well, so that works fine. All of our buffer exchange platforms can work with a lot of up to 100 mg, or not up to, excuse me, can work with a lot of 100 mg per mil solutions and even higher. Obviously, this is going to be before you just put it into either before you put it into the syringes or after you push it out of the syringes. We can't really measure the concentration of something while it's still in the syringe. That's a little bit tricky to do. So, outside of the syringe, it works great. And 100 mg per mil, actually even higher. So, for example, Stunner is actually set up to go up to, depending on the exact protein, can go up to like 275 mg per mil. So quite a bit higher than that 100 mg per mil. So yeah, all of our systems that are shown here are compatible with those higher concentration samples.
Perfect, thank you very much. Do Honeybun and Unagi use for pressure?
Right, so both like we discussed, Honeybun and Unagi are both pressure driven. So in the case of Unagi, we tend to just run it off of either clean dry air or nitrogen. So that's no problem at all. Then that's for Unagi and also for Big Tuna, actually. Honeybun has actually kind of a specific requirement for its air quality, free of oils and particulates. It's got some ISO number that is very long, and I haven't committed to memory, or you can run it off of nitrogen. And we've also actually run them off of air compressors, but those tend to get a little bit loud. So if you probably will be able to contact your facilities manager, ask them, hey, what kind of house air do we have? And then contact us, and we'll be able to figure out if that's going to be, appropriate, or if we might need to, set up some kind of filtration, air filtering system before piping it into Unagi. But we've had customers who've dealt with that loads of times. We've dealt with that loads of times, and it's really no problem at all.
Perfect. Thank you very, very much. Can I integrate your instruments into my lab automation?
Sure. Actually, yeah. So Stunner is totally compatible with integrating it into a wide variety of lab automation solutions. We've done it for pretty much every manufacturer of lab automation out there. And we've also integrated it with our own lab automation systems since we have those, the Big Kahuna being the one that's the fully customizable option. Big Tuna as well. We've had success with integrating that with various types of lab automation. With Honeybun, Uncle, and Unagi, it's a little bit trickier. They're more optimized for just benchtop uses. We've definitely had people who have figured out how to load the unis for Uncle using lab automation, but just because of the way you handle it, they're really more set up for doing just manual handling of samples. So With Stunner, yes, lab automation. Big Tuna, yes, we have some lab automation experience with that as well. Unagi, Uncle, and Honeybun, not quite as much.
Thank you.
But you know what? Our PD team is always working on stuff that's new. They don't tell me everything that they're doing. So who knows? In the future, we'll see what happens.
Perfect, thank you. I'd just like to remind everybody to use the Q&A function to submit any questions that they have. Ross is very eager to answer them. Can I measure multiple shear rates on Honeybun?
Yeah, so anybody who's done rheometry before knows that viscosity will, sometimes change a little bit as that shear rate increases. The really cool thing about Honeybun is it actually does a shear rate sweep during every single one of its runs. So it pressurizes the sample and it increases that pressure over the course of the run, which increases the shear stress as well as increasing the shear rate. So you actually get these nice little curves for that plot the shear rate versus shear stress. That's useful if you've got samples that are non-Newtonian, that either undergo shear thickening or shear thinning. You can actually see that in those curves. It's a great option. And if there is so that's a great option for looking at non-Newtonian samples. Most of the samples that I've handled are Newtonian, so it just gives a horizontal line, very consistent. So you get a single viscosity value after that.
Perfect, thank you. I do actually have a question from one of my colleagues that couldn't make it today, so I hope you don't mind me asking that.
Sure.
How do you combat the potential enhanced aggregation and increased viscosity of the high concentration protein formulation?
So, there are tons of excipients that get added. There's also a whole line of research and investigation in making mutations to proteins and antibodies in order to reduce their aggregation potential. I think that's called mutating out the aggregation hotspots of a protein. So you can do it from the protein engineering side of things, or you can do it from what we talked about today, which is from the formulation side of things. So certain excipients will tend to reduce the propensity to aggregate of monoclonal antibodies, even at high concentrations. We saw data today where sucrose was actually really good about that relative to sodium chloride. Also, in certain cases, adding arginine can help do that. Changing buffer around as well. So pH has an enormous amount to do with whether or not a protein is likely to aggregate. So that's another aspect that we've definitely looked at, and we've done tests of pretty much all of those with Uncle and with Honeybun, doing pH screens, doing excipient screens, looking at different buffers, all of that, and even looking at protein engineering. In fact, actually, just I believe in August there was a paper coming from Q2, one of the Q2 labs that found a fab, was looking at a fab platform and identifying the fabs that were least likely to aggregate, and did that in part using Uncle results. So that may have been a little bit more detailed than necessarily your colleague wanted, Chloe, but hopefully it was useful.
Yeah, I'm sure she'll appreciate it. Thank you very much. We have another question. So can Uncle be used for vaccine formulation development? The conclusion of antigen is in micrograms.
I think that that particular person meant concentration of the antigen is in micrograms, and I'm assuming that's micrograms per milliliter. Depending on its overall fluorescence behaviors, the answer is maybe. But also because Uncle does that has that full spectrum fluorescence, we can also use fluorescent dyes like Cipro Orange or ANS or CPM. Those are all just fluorescent dye molecules that have been used for looking at the thermal stability of various molecules. When you're using dye indicators, so there's some disadvantages to them, but the big advantage is that they can increase the sensitivity of Uncle's assays. In some cases, again, it depends a lot on the specific use cases, specific conditions, but it's something that we can definitely test. It's something that has worked in the past. So if that customer or that questioner is interested in that, we'll definitely have somebody reach out to them.
Perfect. Thank you very much. What is the particle size range for the polydispersity calculation? How does this compare to a standalone DLS or a MALS instrument?
Right. So the particle range for Stoner and for Uncle's DLS is 0.1 nanometers up to 1,000 nanometers. And that's typical for most DLS and most multi-angle light scattering systems as well. Stunner is actually what we call a rattles system. So that's rotational angle DLS. So it's a single set of DLS optics that actually rotates around the sample in order to measure the light scattering at a bunch of different angles. When we doing that doesn't really increase the particle range, but what it does do is get much better sensitivity of those of those larger particles. So where before, with a single DLS system or cuvette-based DLS system, you might just see a single peak that's really wide. With Stunner's rattles, you might be able to actually see, for larger particles, you'll be able to see discrete populations. So a little bit better sensitivity at at that larger range.
Perfect. Thank you very much. I have another question actually. So how could you utilize AI ML to help optimize the research and planning stages? Would you utilize it differently for proteins versus antibodies?
So I don't have very much experience doing AI or machine learning research. There are tons of companies out there in the world that are doing that, have far more expertise than I have. However, what I can say is that a lot of those companies, a lot of those people who are working in that space have been using thermal stability data from UNCLE, as well as KDB22 data from Stunner, and integrating that into their machine learning algorithms in order to predict what's going to be the most stable formulation or what identify mutations that are going to be stabilizing mutations for both proteins and for monoclonal antibodies. I think the biggest, since antibodies are a lot bigger than proteins, there's probably going to be a lot more both options and complexity for antibodies versus your average recombinant protein in that situation. But you can still apply the same types of data in both of those systems. But when you've got 150,000 Daltons worth of protein to mutate rather than say 50 Daltons, you get a little bit more options for customization.
Perfect. Thank you very much. Just like to remind everybody again to submit their questions using the Q&A feature. I have another question from my colleague. I hope you don't mind. It's a bit of a long one.
Sure.
So, as stability is a high concern for monoclonal antibodies, when working in both high and low concentration formulations, how do you propose navigating the management of the viscosity and the stability in each of these cases?
Mm-hmm. So again, it really depends on the specific use case for the customer. So, I think probably the biggest thing to do is reformulate. That tends to be what I see, is that if there is here's what I do and what I have done, and actually what I did in this case study, looked at the KD and B22 values of the lower concentration samples in whatever formulation you're looking at. That'll tell you if the sample is likely to aggregate as you go to a higher concentration. That'll help you at least weed out formulations or variants that are most likely to be unstable, or have a higher propensity to aggregate. And then once you weed out the really bad performers, then you can go increase the concentrations in a small pilot study and look at UNCLE and at Honeybun. They use little enough volume that usually you can push that concentration up high enough in order to get some valuable data there. And then at that point, hopefully you'll be able to find a formulation that is really good for the viscosity and prevents aggregation at higher concentrations. If not, there's lots of research into which specific combination to look at of excipients or mutations. There's lots of literature on that and lots of advice you can find.
Brilliant. Thank you very much. So I have another question. So which instrument is better for KD and B22 measurement, Stunner or UNCLE, and why?
So both instruments are going to give you pretty similar results. They're both perfectly sufficient for measuring B22 and KD. There is a designated app in UNCLE and in Stunner for doing both KD and B22. I personally prefer to do it in Stunner. And the reason for that really is just because Stunner measures the concentration of the samples for me. So I don't have to be nearly as concerned with doing really accurate dilution series. I can afford to be, a little sloppier. Whereas with UNCLE, you actually have to tell it what the concentrations are. However, if you do, I've compared them side by side, they give very similar results. The only advantage of Stunner really is, the only reason to use Stunner, slightly lower volumes, although whether 2 to 9 microliters is important, that's up to each individual user. And then Stunner also measuring those concentrations makes it a little bit easier, at least in my mind, for doing that. But like I said, Uncle can do KD and P22, and if that's what you have, it's perfectly effective. And I've done it as part of these studies. The other nice thing on the other side with Uncle, the other nice thing is you can actually do that KD-B22 study first, since it's non-destructive, and then start doing your TMTAG. So you actually get KD and TMTAG data out of a single set of samples, which can be very valuable if time is at a premium.
Perfect. Thank you very much. So we have another question. So can Uncle be used when protein is bound to adjuvant, like alum? Will there be any interference in the readout?
So I'm actually not quite sure what the question there meant by alum. So I'm not sure I can really answer that, but we definitely have tested Uncle with certain adjuvants, and actually even we've done some studies in which we've actually had ligands mixed in with an enzyme and looked at the thermal stability of the combination of ligand and enzyme, and compared that to different concentrations of the ligand, and that's worked great. So depending on what the adjuvant is, yes, Uncle can work, but I'm not exactly sure what that customer meant by alum. So we'll have to discuss that with them perhaps another time.
Perfect. Sounds good. Thank you very much. So this may be a question running off from the GMP suitability that we mentioned earlier. So have many of these instruments been used to generate formulation screening data that has successfully been used to support regulatory submission sections?
Yes. So I don't, there's not really much more to say than that. So yes, it's our customers have absolutely successfully submitted, FDA have gotten FDA approvals as a result of doing experiments really with all of our, with most of our instruments. Honeyman may still be a little bit too new to have really gotten there. But we have a ton of published articles using all of our instruments on our website. So if there's a specific instrument that you're curious about, there's tons of literature out there of people using it successfully for regulatory submissions, and we probably will be able to provide some specific examples if directly to that person.
Perfect. Thank you very much. I'd just like to ask everybody if they have any last questions to ask Ross. Please do submit them using the Q&A feature. And in the meantime, I don't know, Ross, if you have any kind of common questions that you tend to get asked, whether you'd like to answer them now.
Yeah, so a lot of people ask me what is my favorite instrument, since I do support so many of them. Usually what I'll say is Uncle, because it does give so many options. It's such a versatile, such a flexible instrument. I've done all kinds of experiments, all kinds of even wacky experiments, looking at viral capsid stability, looking at LNP stability, membrane stability of proteins, using fluorescent dyes, using the DLS and thermal ramping options. So it's so flexible. There's so many different things you can do with it. And it really gives me an opportunity to let my imagination run wild a little bit to see what I might be able to do. And once in a while, it turns out to be something quite useful.
Perfect. Thank you very much. Just leave a couple more minutes unless there's any other questions for Ross today. I'm sure he'd love to answer them. If not, you can obviously follow up with them after the webinar. But yeah, if you have any now, you can send your answers anonymously as well if you'd like. Give it another. Okay, I think we'll end it there. Thank you so much for your presentation, Ross. I really do appreciate it. And as mentioned, the on-demand webinar recording will be made available over the coming days. So please look out for this in your inboxes.
Yep. All right. Yeah. Thank you, Chloe. Thanks everybody for joining me. And yeah, hope you have a good rest of your day.
Perfect. Thank you, everybody. Bye.